Okay, we study X23NQ, temperature and heat. You can download this PDF file from our digital library of KPOP. If you visit kpop.org, you can click X series. This is X23, temperature and heat. The main textbook is here. If you click X, you will download this. And if you click this, you can watch the
이번
lecture given
시간은
in Korean.
온도,
And if you click this, then you can watch the
From this
lecture
class
given in
come to the end
English.
of this.
And you can return to the library. Or you can subscribe YouTube channel or of our K-pop collaboration. Okay, let's begin. List the fundamental particles. From today on, we are studying statistical physics. That is to describe the macroscopic behavior of identical particles and mainly the molecules. Okay, so in fact, molecules are relatively stable, but they are not fundamental particles. The fundamental particles that construct the nature are listed below. A fundamental particle does not have any substructure in it, so it cannot be broken into pieces. Hence, we cannot break it into pieces. All right. Such particles are quarks, leptons, and gauge bosons. There are elementary particles that form the whole universe. Let's see. A nucleon, such as a proton and a neutron, they are constructing a nucleus. And the nucleus, okay, let's just stop here. Consider what's that nucleus? Proton or neutron is a nucleon, and nucleon is a substructure, elementary substructure of a nucleus. Nucleon consists of three quarks. For example, up this proton consists of up, down quarks, three quark state. Neutron, up, down. But up and down, these are two quarks. However, that's not all. So we have up, down, charm, strange, top, and bottom. There are six kinds of quarks. However, in nature, there are particles has the equal mass but opposite charge. They are called antiparticles. So U bar, D bar, C bar, S bar, T bar, B bar. They are antiparticles of up, down, charm, strange, top, and bottom. All right. Next, we consider leptons. Leptons, you know very well about electron, but electron is not the only leptons, and there are more. Muon, tau, they are all leptons, but they are heavier than an electron. Another particle, antiparticle, the same mass as the electron, but opposite charge, there exists such kind of particle that is a positron. So we have mu1 that is negatively charged, but we have mu plus that is the antiparticle of mu minus. Tau also, we have tau minus, and it's an antiparticle, tau plus. The gauge bosons mediate fundamental interactions. Electromagnetic force is transmitted by this carrier of force called the photon. In fact, it is generalized to have an electroweak theory that has weak interaction in it. The unification of the electromagnetic interaction is due to the Faraday's law that involves the exchange of the transformation of the electric field and magnetic field. So because of that, Maxwell's equations state that the electricity and magnetism, they can be unified. The Einstein's special theory of relativity made us to construct a theory that involves both electricity and magnetism. So unification of the electromagnetic theory was possible because of Einstein's special theory of relativity. And then we know these kind of quarks, they are hidden inside nucleus. And in a nucleus of an atom, there are multiple protons and neutrons. But the reason why they are bound together, even if the Coulomb repulsion is extremely large, should be extremely large according to what we learned. By the way, in the substructure of the subatomic regime, the electromagnetic interaction is negligible in comparison with the nuclear force that consists of weak interaction and strong interaction. The weak interaction is exchanged by these carriers of force called weak gauge bosons, W plus minus, and Z0, that is neutral, electrically neutral. The strong interaction among the quarks is due to the existence of the gluon, that is a gauge boson of the strong interaction, because this W has an electric charge. It has its own interaction with the other gauge bosons. In addition, gluon has its own charge. So there are 8 kinds of gluons because of color that is independent of color that we see with our bare eyes. The gluons interact each other as well as with the quarks. So the nature consists of these kind of things. But if we are interested in the temperature of usual gas that you encounter in everyday life, then you don't have to worry too much about the substructure of an atom. So let us focus on the molecule from now on. Okay, molecule consists of atoms. An atom consists of nucleus and surrounding electrons, the bound state of positively charged nucleus and electrons. And the reason why the Coulomb interaction does not break the nucleus is the existence of subnuclear force that are weak interaction and strong interaction. But for the time being, we just forget about the detail of the particle physics. Number two, list additive physical quantities. If you study thermodynamics, you will encounter various variables that is closely related to classical mechanics of a single particle. But if you are interested in the average of the behavior of many molecules, you sometimes add some physical quantity algebraically without difficulty. However, in some case, you need to take the average. So average sum, sometimes it's not uh, simply defined. As you should be very careful about the weighting factor in averaging process. So here I say that additive physical quantities are the quantities that can be added without worrying too much. There are two particles of masses m1 and m2. What is the total mass of the system? Just a simple algebraic sum. So we can say the mass is an additive physical quantity. Energy of a particle under conservative force is the sum of the kinetic energy and the potential energy. So this energy can also be added together. Okay, total mechanical energy and the sum of the total mechanical energy of many particles. Okay, that's fine. So we can define the sum. Any field, such as electric field, gravitational field, they can also be added according to the superposition principle. In addition, if you have wave, the sum of waves, we say the resultant wave is a simple algebraic sum of the waves. Okay, that's fine. But there are some quantities we should be very careful with dealing with. Okay, the following quantities are defined as a ratio of the two physical quantities. Okay, there is a still sample of mass m1 at temperature T1 in equilibrium. Another still sample of mass m2 in thermal equilibrium at temperature T2. If the two samples are in thermal equilibrium without any heat exchange or with the environment, then the final temperature is not simply the algebraic sum of these two. We should be very careful about this. For example, if you compute the average, you need to be very careful. Okay, we will consider these kind of things later in more detail. Number three, what is the temperature? The standard physical definition of temperature T is the average kinetic energy of elementary particles, elementary in many cases, identical elementary particles, and these elementary particles are assumed to be molecules in units of Boltzmann constant, remember. So this is kinetic energy of the ith particle in a set of molecules where I is an identifier running from 1 to n. So we sum all of the kinetic energy and then divide it by the number of particles to find what? Find the average value of the kinetic energy. And then in units of the Boltzmann constant. Okay, this is the Boltzmann constant. You can see the Boltzmann constant is in units of energy divided by Kelvin. That represents the absolute temperature. In addition, for simplicity of calculation, we introduce a pure number. Later, we will find what is the best choice of this dimensionless parameter lambda later. Okay, anyway, the SI unit of temperature, this is Kelvin. All right, and it is strictly proportional to the average value of the kinetic energy of the whole system. The total kinetic energy of a system of n particles is we learned in classical mechanics, n-body system or rigid body motion. We learned that can be expressed as a sum of kinetic energy of a single particle whose mass is the total mass of the whole system and whose velocity is the velocity of the center of mass of the whole system. That is called the translational kinetic energy. In addition, we have additional kinetic energy relative to the center of mass. So every particle's position can be expressed as in the CM frame. Then x bar is the position vector at the CM frame at which the center of mass is at the origin. So if we choose the frame of reference to be the center of mass frame, when you consider n particle system, n identical particle system consisting of molecules, then you usually choose the CM frame in which you can ignore this, and it is absolutely zero, and you just consider the relative velocity of every particle, and their velocity squared multiplied by 1/2 mass of that particle and sum over all particles, you will find the total kinetic energy of the n particle system. All right, so from this definition, if you remove this at the center of mass frame, you will find this value has a certain minimum value. If everything doesn't move at all, velocity is zero for every particle, then this temperature must vanish. So, and never less. This is the minimum possible value of this temperature that is called absolute zero. Absolute zero means everything is frozen. Everything frozen means everything does not move at all. Okay, that's it for today. Thank you.